Welcome back. Today we'll be talking about proportions in a special supplement. You won't find a chapter matching this or a subchapter in Andy Field's book if you're following along in the textbook, but it's an important thing to address. Up until now, we've basically treated proportions like any other interval variable as a kind of mean, which they are in a sense, and we've calculated statistics for them the same way as an interval variable. While that'll usually get us close to the right answer, it's not actually correct. Because you see, unlike an interval variable, a proportion has both a limited range, it goes from 0 to 1, and we know that all the categories, that is x and not x, will add up to 1. In everyday terms, you can't have less than 0% or more than 100% of people, at least unless you're talking to a sportscaster. And 100% of people fall into either the x or not x category. Now, because of this, there are some differences in how the statistics are computed for proportions. Specifically, the standard error of a sample proportion, I've written it out here in the middle, is equal to the square root of p hat, you can hardly see the hat, but that's the sample proportion, p hat times 1 minus p hat, so the proportion x, the proportion not x, divided by the sample size. Note, even though it's a sample, we're not using the n minus 1 because we know, because with the proportion, the standard deviations are a little different. In fact, the standard error of a proportion is the same thing as the standard deviation of the proportion. This square root might be a q. So if you see that, it's basically the same thing. Usually we talk about the standard error for a proportion. And if you were to talk about the variance of a proportion, we don't normally do that at this point, but it would be the square of that. We would just take out the square root. Essentially what this means, though, this p hat times 1 minus p hat, what this means is that the closer a proportion is to 50%, the less certain we are of it, and the higher its standard error. If you think about the normal probability distribution, that makes sense because the area close to 50%, if this is a normal probability distribution down here, see we've got -3, -2, -1, 0 for z-scores, you can see the cumulative percent adds up very slowly at the left tail until it gets to the middle, and then between -1 and 0, well over half of that side are already there. So even a small change in the value can mean a large change in the number of people. Thus, when we're close to about half the population, which is what we would guess if we didn't have any data for a proportion, right? We would say half are this and half are that if we didn't have any data. So the closer that is to 0.5 or 50%, the less difference there is in the sample proportions x and not x, and the more uncertainty we have to build in. What this means in practice is that you can compute a confidence interval of a proportion the same way you could compute a confidence interval of a quantity, except that you would use the standard error of the proportion instead of these other two formulas we've got at the top, which both boil down to the standard deviation divided by the square root of n, but one has the sum of squares divided by the sample size for if we know a population standard deviation. The other would be the sum of squares divided by the sample size minus 1, and then all over root n. Just as a reminder in case you'd forgotten, and to see the comparison there. For example, we can take a proportion of 0.8 up here, 80%, sample size of 100. To calculate the standard error, it would be the square root of 0.8, that's the proportion, times 0.2, 1 minus the proportion divided by 100. Which is the square root of 0.16 over 100, which comes out to 0.04. So if the standard error is 0.04 and we wanted to compute a 95% confidence interval of that proportion, the proportion of people say that answered a question as yes, we would do the same thing we normally do. We would take a z-score of -1.96 to +1.96. So we take 1.96 times the standard error and subtract it and add it, we'd end up with a confidence interval of 0.7216 to 0.8784. To recap, the confidence interval of a statistic is always the statistic's value, the mean, the proportion, etc., plus or minus a critical value, for us a z or a t-score, for the confidence level times the standard error. But we've learned 3 different formulas for standard error. One that applies when we know the population standard deviation and we're calculating it for a quantity. One that applies when we're calculating it for an interval variable, a quantity, but we don't know the population standard deviation, the more common case. And finally, what we learned today, the standard error of a proportion. That formula for the confidence interval is always going to be the same, as long as you know the standard error. So hopefully that helps you to get a grasp on the differences and the similarities between proportions and other quantities in terms of how we calculate them. Thanks for watching. Hopefully this has helped you learn some things. Have a great day.